Hello everyone, thank you all for coming. My name is Caleb.
I'm Cameron.
And we're going to be talking to you today about primordial signatures of the early universe in the cosmic microwave background.
So our research, to give you a little background on what the CMB is, in 1965, two radio astronomers were using a microwave telescope to look at deep space objects. And they found that they were getting a signal that was almost uniform from all directions wherever they pointed the telescope. And initially they thought that there was something either wrong with the telescope or they needed to be cleaned or something. But what they initially, finally what physicists realized was they were actually detecting a signal from space itself. And they realized that this was a signal of the early universe about 380,000 years after the Big Bang. And so what this showed was at that time the universe was nearly homogeneous, and then greater resolution on the telescopes and a better sensitivity has shown that it wasn't quite homogeneous. You have these patches of higher and lower temperature, and that corresponds to a higher amount of mass in the colder portions and a lower amount of mass in the higher portions. And so with that information we could go forward and the universe was not as homogeneous as we thought.
So basically what happens here is that we have the Big Bang, and then it expands rapidly through inflation. The universe expands, and basically imagine the size of an atomic nucleus. And it expands to the size of the entire observable universe in 10 to the minus 30 seconds. And while this is happening, not only is the universe expanding, but also the quantum fluctuations are also stretching through time. And these quantum fluctuations are seen through the red and blue spots where the hot and cold regions are. So the universe expands, the quantum fluctuations, they stretch out, and at the very beginning of the universe, everything's microscopic. Whenever the Big Bang occurs, it inflates extremely rapidly and everything becomes macroscopic. These quantum fluctuations, they no longer act under a quantum mechanical manner, instead they're macroscopic. So, like Cameron said, the image of the cosmic microwave background that we have is about 380,000 years after the beginning of the Big Bang. Now, what's the main purpose of this? What is our goal? Well, we want to take theory and all the models that we have and calculations to basically take this and extrapolate further back in time to further understand the inflationary period of the universe expanding and just moments after the Big Bang. And as you can see, the scale here, the universe expands extremely quickly, 10 to the minus 32 seconds right there.
All right, so one thing we had to take into consideration was our scale factor. So this takes into consideration the expansion itself. So here at the Big Bang, there is no distance between the objects. Everything is right on top of each other. But right after the Big Bang, it starts expanding, things start moving away. And then here, the inflationary period begins, and when that happens, everything moves away or from each other rapidly. And so this boundary right here, where inflation begins, is kind of where those quantum fluctuations were frozen and where we kind of focus our attention. This is just some of the work we did, just to kind of give a taste. We spent a couple of weeks just working this out by hand. It was not
Yeah, this is just a few images. This is just a few images of dozens of pages of work that we worked on. In the physics suite, we filled up both the boards with all types of work, and we basically focused mostly on these equations.
So taking those equations that we ended up with, we can make this graph. So this is a graph of the amplitude of the fluctuations versus the inverse of the wavelength in terms of the Hubble constant. And so we found this area here where the size was really dampened. And then this graph over here gives a breakdown of the temperature fluctuations, again, in terms of the wavelength. Kind of in the same way that you would see like a sound engineer take like a sound bite and break it down into the individual parts. And so this area here, you can see the data points don't match up super great with the model. So we were hoping that this suppression could give rise to why these data points don't quite match up.
And the main reason why they don't exactly match up is because as you go further down the graph, there's larger and larger scales. And that's why the data points don't fit exactly with the theory and the model. So basically our main conclusions are we are studying the cosmic microwave background and we want to get an idea of, you know, the beginning of the universe, how the nature of the universe, you know, changed after the Big Bang.
And our project specifically looked at quantum signatures of the pre-inflationary universe and the impact that can have on the cosmic microwave background spectrum.
And like I said, this might explain the poor fit of the existing theory that we have due to the large scales. And thank you all for coming.
Any questions?
Any?
So did you collect the data from the Wofford Large Diameter Radio Telescope that we have in our backyard?
Previous research, we unfortunately did not have that access.
Can you talk a little bit about the time axis? It looks like it's scaled with the Hubble constant, or what did you use there? Is
Yes,
that a
this
feet?
is the inverse of the wavelength of the fluctuations. So in the momentum, it's scaled with the Hubble constant, yes.
Okay. And so, can you tell us a little bit more, like how we should think about that?
I think it's the wavelength, I think, of the photons we're receiving, so of the signatures. I believe that it's similar to P as actually it's a momentum, but on that scale, momentum and wavelength are kind of the same. So it's that just the energy of the.
When you say the data doesn't fit, I see you drawing a circle around on that.
Yeah, it's just these. So these are individual data points, and then the red line is itself the model. So here, around here, you can see like all the data points line up with the model, but down here, there's a lot of data points that are off the model.
And so if I look on the far right, they're not on it, but I guess the error bars is included. So the data on the far left, the error bars are small enough for you to say they don't fit the model.
Yeah.
I couldn't see that.
Yeah, those little blips, those are the error bars themselves. So obviously on the right side, the error bars, they kind of fit close to the model, but over here, they don't fit as well as the other data points.
Okay, so as a person who understood like half of what you said,
Yeah.
and knows nothing about physics, what's like the overall significance or importance of this type of research? Like what's y'all's?
Yeah, so kind of what we're trying to do is, so we can get a direct signature of the cosmic microwave background with a telescope, and kind of our research was trying to show that you can look at a time right here, right before, like right after the Big Bang occurred, and extrapolate the data from the cosmic microwave background to know kind of how the early, get some signatures of the early universe.
So we're doing time
One more question? Go ahead.
Yeah.
I was just curious why one of those sections is labeled the Dark Ages and then that may be going on.
I think what's happening in here, this is after what we featured. I think what's happening here is there is something that's preventing us from getting any data from there. I'm not sure if it's a consequence of the universe or something later on, but there's just no way to get any kind of these signatures.
So you don't have stars and stuff forming, so you don't have light being mixed during that period.
All right. Oh, one more? Go ahead.
This is a quick one.
Yep, go ahead.
The equations, are those based on general relativity, quantum mechanics, the equations you were working with?
I think they're quantum field theory, so a little bit of quantum mechanics and special relativity.
And GR.
And GR.
And GR.
All right, thank you.